Hey kids, how's it going? This is Mr. Hill, and I'm going to share something really cool with you. Look on the right side of your screen in the hexagon. You'll see a cool little picture right here. Now, it doesn't look like much right now, but this might be the key to us being able to go to Mars and stay there for a little while. Okay. So over here on the right side of the screen, a little hexagon, that is a sheet of purified boron nitride nanotubes. It is very, very lightweight, um, but it's very, very strong, 10 times stronger than steel. But first, let's start the very first episode of science stuff that blows kids' minds. Okay. Okay. So, this link that I have here on the screen is also on your worksheet. If you type that into a browser, it'll take you to a video by Neil deGrasse Tyson, where he talks about the rocket equation. What is the rocket equation? Because you have to account for the weight of the fuel itself. So, say you had a rocket. I'm going to try and draw one right here. Okay. Say you got a rocket right here. It's the wings. Yeah, I know it's bad, but hey, I'm not an artist. Okay. At the very tip up here, you have astronauts and you have payload. All the rest of this little piece right here, that is the astronauts plus payload. All the rest of this is fuel. Why do they need so much fuel? And if you click on that link, he explains to you why they need so much fuel because not only do you have to have enough fuel to get the payload into space, and we all know that when the spacecraft come back to the atmosphere of a planet, it compresses the air in front of it, and compressed air gets really, really hot, and you also have some friction involved as well. So you need something to be able to get your spacecraft back into the atmosphere without burning up like a shooting star. These boron nitride nanotubes can be part of heat heat shield on the front of spacecraft that dissipates heat to the sides as the spacecraft re-enters the atmosphere. Is another important property of boron nitride nanotubes. It is radiation shielding. It one of the big sources of radiation in space are neutrons, and boron nitride nanotubes block neutrons, um, and which is a big hindrance to getting humans to be able to stay in space for long periods of time. Is the radiation poisoning from from the sun and other sources of radiation out in space. If we can block a lot of that, we'll be able to stay in space longer. Remember, we don't just want to go to Mars, we want to be able to stay there for a while, maybe perhaps even terraform it. So let's go ahead and draw a sun. And you guys on your worksheet, you can also draw on your worksheet wherever you like. And I want to draw a big sun over here and draw the sun rays. Yes, everyone has to draw. You don't have to be a great artist, as you can see. Mr. Hill isn't one either. Okay. But the radiation coming from the sun can be bad for the health of astronauts. Okay. Yes, I'm not an artist, but this is my astronaut. You can tell by the big boots. Okay. All right. I'm sure your drawings are going to be a lot better. and that's fine. Um, as a matter of fact, if your drawings are much better than mine, I'm going to steal them and put them on my presentation and say that I draw. All right, that's only fair. Okay, let's keep going. All right. You would think that something that strong, that's 10 times stronger than steel, would be something that is really tough looking, but it's not. It's more fluff looking than tough looking. Draw. They look like puff balls. They look like cotton balls, actually. Okay, nice and fluffy. And here at Rice, we had several of them in jars. Okay, and this is a jar of the nanotubes. Okay, you want to see what it actually looks like? Okay, I will show you. If it allows me to. Okay, and that's what it looks like. Let me erase my drawing. Looks like cotton, doesn't it? It's like regular old cotton, but it is perhaps one of the strongest substances on the planet. Okay, so we take that cotton or that cotton-looking stuff, those boron nitride nanotubes, and we mix it with what's called a surfactant, similar to soap, and we spin it in a machine called a speed mixer. I'll try and draw this speed mixer. The speed mixer, the coolest thing in my opinion, has this little robot, little square robot on it, and all it does is hit the go button. Okay, and the go button is right here. It has a lid on it as well. You lift the lid, and there's a compartment inside where you stick your you stick your canister of boron nitride nanotubes and surfactant inside of it, and it spins for hours and hours and hours. The robot keeps hitting the start button because it only does it at 5 minutes at a time. We have to do it like 2 or 3 hours. And when it's done, it comes together and looks like glue. First, let me show you. Let's show you what it looks like. There's the speed mixer right there. The lid is up at the top, right over here. And here's a little robot. The little white thing is a robot. And all it does is hit the button, the start button underneath it. And it's set to 5 minutes. You can see it on the screen right here. 5 minutes. And it keeps hitting it over and over again. So you don't have to keep hitting it over and over again. The robot does it for you. All right. Let's keep on rolling. Okay. Seeing double. Okay, what does that mean? Well, you can tell you have boron nitride nanotubes because when they line up just right, they do this thing called birefringence. What? Birefringence. Birefringence. Well, first here's the glue-looking substance right here. Looks like Elmer's glue, but it's not. Looks like glue. Okay. And so here's the tube. And here here's the glue inside of it, the glue looking stuff inside of it. Okay. But when they line up, those tubes line up just right, they form what's called liquid crystals. Once we take that glue looking substance and we suck it up in this little pipette right here, it's a little glass tube, very, very fragile. It's really hard to do that. You have a syringe like this, and it has a plunger on it, just like the syringes that they give you a shot with. And we attach a little tiny glass tube to it called a capillary. We use that to suck up the glue looking stuff, and then we break the capillary off right up here, put it under a torch to melt both sides of it down. Then we take that broken piece of glass and we take it to this cool thing right over here called a polarized optical microscope, or a POM. Now, Mr. Hill can't draw that. Okay, I'm gonna let some of you guys are great artists, I'm gonna let some of you guys draw that. Okay. This blue thing on top of the microscope is a computer. It sends a signal to an actual computer. Back here, you see the screen of it a little bit behind there. You can look at the image on the computer screen. Here's one of the images of the milky looking stuff that's in the capillary, the little piece of glass. If you look closely, you can see little lines. Let me use a different color so you can see it better. You see little lines inside of it. When molecules or particles line up in an orderly fashion, they're called crystals. In a solid, it's pretty easy to tell that you have a crystal because they look a certain way. They look glassy and like diamonds or amethyst and stuff like that. In a liquid, liquids can form liquid crystals as well. Okay, and as a soft solid, colloids like egg whites are also soft solids. We'll talk about those later. Okay, but when they line up just right, they will cast two reflections, and that's what's called birefringence. They'll cast two reflections. To help that happen, we have to take the sample and put it in this thing here. It's called a sonicator. And it blasts your sample with sound, which also makes them line up the way you like. Another sample. Oh, this is the computer that's connected to the microscope. You put it, when you take your new sample, put it back in the palm, the polarized optical microscope, and it lights up. How cool is that? This picture was taken of a sample done by a young guy I was working with named Josel Reyes. See the smooth curved lines. Let me point these out for you. The smooth curved lines. That is evidence of birefringence, which means there's evidence of liquid crystals there. You see that? That means you probably have boron, nitride nanotubes. These dark spots right here are impurities, like elemental boron, where we want boron nitride. But you get boron all by itself, elemental boron, that forms an impurity. You might have some sheets as well. Sheets are when um, The boron nitride comes together, but it doesn't come together as tubes. It comes together as sheets instead. Okay, just the way the architecture of the way they come together changes the properties of them. So you got to have them in a tube fashion to get the same properties. All right. Okay, so let's take a look at the next thing. The next thing is trying to get as pure a sample as possible. To do that, put them in a different type of sonicator. This big sonicator has a needle in it, a big needle that you stick your jar of substance in, and it shoots sound waves through it to also make it line up even better. And then you put it in a centrifuge. It's similar to the speed mixer, but it has to be balanced because it goes at such high speeds. You put your sample on one side and put something of equal mass on the other side, or it'll be unbalanced like your dryer at your home. Okay, you can't put all the clothes on one side, it'll start shaking and getting real violent. Okay, we don't want that. Okay. Have this been in the centrifuge for a few hours. Then it will separate. The more dense stuff will separate and form a solid at the bottom. This is called pellet. Pellet is the solid, the stuff we're not going to use, that collects at the bottom. And floating around it is the liquid that we are going to use. And that liquid is called permeate. Permeate. And let's take a look at this permeate. That's the liquid permeate right there. Okay. Then the coolest part. My mentor showed me this thing that looks like a cup, but the cup had an opening on both sides. I'm like, what kind of cup is this? It sounds like a very inefficient cup. Okay, but um, one side of the cup is connected to a filter, a semi-permeable filter that lets water through, but it traps the boron nitride nanotubes. Oops. And it was attached to a flask like this, and a hose was attached to this side of the tube. That hose was attached to a pump. That's with had a handle on it, that pumped all the air out of this section, which forced the water from your solution, from your permeate, through the little filter, leaving nothing but the boron nitride nanotubes stuck to that filter right here. Okay. So and there's the setup. Here's the glass with no bottom. The filter is between this clamp right here. And here is the flask with the glass tube on the end, and you can see the red tubing going from there to this vacuum pump. Okay. Then Once you've done that, once you did that, you wind up with a sheet of boron nitride nanotubes. Okay. Now on your worksheet, you have the actual pictures on one side, and you have these with the blanks on the other side. Okay. You can draw all of on this side. I'm sure you're a better artist than me, and I'm going to post your pictures around the room. Okay. Have fun with this, and I know you're going to love it. So, but before we go on, let's take a look at the materials and methodology. Okay, just a recap of what happened. Okay, so the fibers and the surfactant are spun for 3 hours in a speed mixer. Capillaries, or little glass tubes of the milky solution, are sonicated and checked for birefringence, which is evidence of liquid crystals. And we took several pictures of them at 15-degree angles: 0, 15, 30, 45, 60, 75, and 90 degrees. Um, and because it's liquid crystals, each picture would look a little bit different, even though you're looking at the same thing. Okay. Then we took the rest of the solution and sonicated it and centrifuged it also for hours. Okay. And the sample is carefully vacuumed through a filter, leaving a highly purified paper-like solid for further analysis. And that is the paper-like solid right there. All right. So now I hope you paid attention, because now it's time for your pop quiz. Go ahead and take your iPad, scan this QR code, and take the test. That's right. And I know you're going to do great on it, because I know you paid attention. All right. Thanks for joining me and sharing in my experience at Rice University. And I'll talk to you later.